ओके. हॅलो स्टुडंट्स. तर आत्तापर्यंत आपण मेट्रिक स्पेस ह्या युनिटमध्ये 2-3 गोष्टी बघितलेल्या आहेत. तर पहिल्यांदा आपण डेफिनेशन बघितलेली आहे. त्याच्यानंतर मेट्रिकच्या काही एक्झाम्पल्स बघितलेले आहेत. मेट्रिक स्पेसच्या काही एक्झाम्पल्स बघितलेल्या आहेत. तर आणि कॅरेक्टरायझेशन आणि कंटिन्युअस फंक्शनची डेफिनेशन बघितलेली आहे. त्याचे काही एक्झाम्पल्स बघितलेले आहेत. त्याच्यानंतर कॅरेक्टरायझेशन ऑफ कंटिन्युअस फंक्शन विथ द हेल्प ऑफ ओपन सेट आणि क्लोज सेट हा एक पॉईंट बघितलेला आहे. त्याच्या रिलेटेड एक्झाम्पल्स बघितलेले आहेत. आता आपल्याला काय त्याच्यावरती काही थेरम्स बघायचे आहेत. आपण ॲक्च्युली एक थेरम बघितलेला आहे. जर एफ हे कंटिन्युअस फंक्शन असेल तर काय प्रूव्ह केलेलं आहे आपण? इनव्हर्स इमेज ऑफ ओपन सेट इज ओपन हा थेरम आपण प्रूव्ह केलेला आहे. ठीक आहे. तर आता आपल्याला काय करायचं आहे, त्याच्या पुढचे काही थेरम्स जे कंटिन्युअस फंक्शन आणि ओपन सेट आणि क्लोज सेट ह्याच्यामधल्या काय रिलेशन आहे याची सांगड घालतील. ठीक आहे. तर त्याच्यामधला आता पहिला थेरम आपण बघतोय. तर पहिल्या थेरमचं स्टेटमेंट काय आहे बघा. व्हॉट इज दॅट थेरम? लेट एक्स d1 and y d2 be two metric spaces. Metric spaces. Then following statements are equivalent. So first statement is f inverse of g is open in x whenever g is open in y. Whenever g is open in y. For every, second statement, for every p belongs to x, for every point p belongs to x, and a sequence xn in x converging to p, then the sequence f of xn converges to f of p, in, and f of p lies in, obviously f of p lies in y. So let us discuss with this proof. So what is the statement? This statement says that these two statement whichever we used, that is we had derived some sequential criteria, and we had derived an characterization. These two statements are equivalent. We are proving this statement that the sequential criteria for the continuous function and the inverse image relation of the continuity function both are same. We will prove in this theorem. So proof. Suppose inverse image of open set is open in X. Suppose, first statement, assume that first, suppose inverse image of open set is open in X. Suppose inverse image of open set is open in X. Let P belongs to X be an arbitrary point, and let xn be a sequence in X such that xn converges to P. To prove that f of xn converges to f of P, let epsilon greater than 0 be given. That is, we have to use the definition of sequence, convergence of sequence, in order to show this. In order to show this, we have to use the definition of convergent sequence, isn't it? So, and in the convergent sequence, for given epsilon, we have to find n such that all these conditions get satisfies. So, let epsilon greater than 0 be given. Then, for that epsilon, the ball b f of p comma epsilon is open in y, and by the hypothesis, inverse image of open set is open, and by using the hypothesis or assumption, by using the assumption, inverse image of this open ball b, open ball with center at f of p and epsilon, is open in X, Note that, or notice that f of p lies in this ball. Note that f of p belongs to the open ball with center at f of p and radius epsilon. This implies that if f of p belongs to this ball, f inverse, or we can say p belongs to f inverse of this ball. May I write? Okay, so p belongs to f inverse of the ball with center at f of p and radius epsilon. So this implies that there exists delta greater than 0, such that the open ball with center at p and radius delta is subset of f inverse of the ball with center at f of p and epsilon. This is why, because this is an open ball with center at p and radius delta, and obviously p belongs to this, and we have proved that p belongs to this. So every point of this belongs to the point of this, hence this relation. This implies that or we can say that, suppose this is an equation number star. Now also xn converges to p, given that, then for this delta greater than 0, there exists n naught belongs to the set of natural number such that distance between all the point x, n and p is less than delta for all n greater than or equal to n naught. This implies that This implies that xn belongs to the ball with center at P and radius delta for all n greater than equal to n naught, which implies that f of xn belongs to the image of this ball P comma delta for all n greater than equal to n naught. This implies that f of xn belongs to the ball with center at f of p and radius epsilon using equation star. This implies that d2 of f of xn and f of p, that is distance between f of xn and f of less than epsilon for all n greater than equal to n naught. This implies that f of xn converges to f of p. That is, we had assumed that inverse image of open set is open, and whenever xn converges to f of p, then we had proved that f of xn converges to f of p. Now we are going to converse statement. That is, we are assuming that whenever xn converges to p, f of xn converges to f of p, and we will prove that inverse image of open set is open. Now conversely, suppose that for any p, belongs to capital X and any sequence xn in capital X such that xn converges to p, then f of xn converges to f of p. Let G be any open set in Y. We have to prove that f inverse of G is open set in X. Now G is open set in Y implies that Y minus G or G complement is closed set in Y. Let capital F is equal to Y minus G. This implies that f bar is equal to f, that is closure of f is equal to f, because f itself is a closed set. Now f inverse of f bar is equal to f inverse of y minus g, which is equal to x minus f inverse of g. Now to show that f inverse of g is open, we will show that x minus f inverse of g is closed. That is, we will prove that f inverse f bar is subset of f inverse of capital F. Now let P belongs to f inverse of capital F bar. This implies that there exists a sequence xn in, there exists a sequence xn in f inverse of capital F such that f of xn converges to f of p. But by hypothesis f of xn should converges to f of p, f of xn converges to f of p, hence xn belongs to f inverse of capital F. This implies f of xn belongs to capital F. This implies that f of p belongs to f bar, which is equal to f, as f is closed. This implies f of p belongs to capital F. Now this implies that p belongs to f inverse of capital F, implies that f inverse of capital F and its closure is subset of f inverse of capital F. This implies that f inverse of capital F is equal to f inverse of capital F and its closure. This implies that f inverse of capital F is closed set in capital X, but f inverse of capital F is nothing but x minus f inverse of G. This implies that f inverse of capital G is open in capital X. Hence we had proved that inverse image of closed set is closed. Inverse image of closed set is closed. Now see some applications of the theorem which we had proved. Among them, first example is, what is that example? Let f from R to R be a continuous function. Be a continuous function. And capital A be a closed set. Capital A be a closed subset of R. Let capital B is equal to all the points of A such that f of x is equal to 0. Then show that B is closed subset of R. Then show that B is closed subset of R. Now if B is empty set, then we're done with our proof. So assume B is non-empty. B is non-empty. And what is F is continuous function. F is continuous function. And what is B? B is the collection of all the elements of A such that f of x is equal to 0. So let us see one figure. This is what R. This is what R. A be a subset of A be a closed subset of R. Here we are collecting those elements. F of x is equal to 0. Suppose 0 is here. And suppose this is my A. Suppose this is my set A. And from A we are collecting those element whose image is 0. Suppose this is are the element x from A who are mapped to 0. Who are mapped to 0. So what is this? This is nothing but F inverse of, if I am writing F inverse of singleton 0, this is what? Collection of all the elements x such that f of x is equal to 0. That is, it is an inverse image of singleton 0. B is nothing but inverse image of singleton 0, and we know that singleton 0 is closed set and F is continuous mapping. So inverse image of closed set is closed, implies that B is closed set. B is closed set. Hence we done with our proof.